let's talk about the scalar equation of planes. And before we get into that, let's just talk about some background knowledge for a moment here. So we have the word that we're using a lot, plane. And plane can be used to describe something like an airplane, or it can be used to describe our flat surface here. And if we look at the etymology of the word, so etymology is like the history or the origin of a word. Yeah, I spelled that right. We're good. So from the Latin, we have the word planum, which means like a flat surface. So from there we get plane, Latin, planum, and or we can have French origin, plane, to mean like geometric plane. And we also talk about that in everyday. So plane has a French origin. And we're talking about this kind of plane, which is just land, which is really flat. Or we talk about the Great Plains, which is like our prairies and stuff out west in Canada, where we have things like buffalo and bison. So wonderful little picture here, a little bit of background, a little bit of flavor. And let's talk about what happens when we have multiple planes. So we've talked before about dealing with our axes in 3 dimensions. So we have our x and our y and our z. But we haven't actually talked about defining the planes really. We've talked a little bit about our xy plane, which is the one that we're used to working with normally, but it's set on its edge here. So we have our xy plane. And we can see here that there's 2 other planes we need to be able to define now too. So we have our xz plane. So xz plane, so kind of defined by the x and z axis, and then our yz plane. So extending along, we're kind of connecting our y-axis and our z-axis, and they extend below as well. I'm just trying not to clutter it up too much. So our y-z plane. And what else do we notice here? Well, these planes can intersect and cross through each other, so that's something we're going to need to talk about. Intersection of planes. And whereas our 2-dimensional plane, like x and y, has 4 quadrants, our x, y, and z planes, our 3 space formed by them, forms 8 octants. And I don't think we're really going to describe it. We're not going to talk, you know how with our cast rule and stuff, we talk about being in quadrant 1, 2, and 3. I think in this course, we don't actually get into like, which octant is this located in? Just know that that is the language used to describe this. So now we're going to look at defining our plane by finding the equation in scalar form. So scalar form is our Cartesian form. We've defined this previously for our lines. In order to define our plane in scalar form, we're going to need a point and a normal vector. And if you've watched our previous video, you'll notice that we already figured out how to find a vector normal to a plane. So that's going to be a useful skill moving forward. And just a quick reminder as well, the other 2 equations we've talked about already are the vector form of a plane or the parametric form. And we recall that in order to form those equations, we needed a few things. We needed a point that lies on the plane, and we needed 2 non-collinear direction or basis vectors, m1 and m2, where m1 was not a scalar multiple of m2. And I don't strictly need to say that again, but for the sake of clarity, and if you're watching this video not immediately after the one that comes before, not a bad idea to go over. So what do we have to say here about the scalar form of our planar equation? Well, we know that the cross product of 2 vectors is always perpendicular to the 2 vectors. For the basis vectors of a plane, any vector perpendicular to the plane is called a normal. And remember, we have our notation for that. We use n for normal, and it's a vector, so it needs its little hat or arrow. And using a normal and any point on the plane, we can construct the scalar form of the plane. So let's go ahead and see what that's going to look like. The scalar form of a plane is written as ax plus by plus cz plus c equals plus z. Let's try that again. Ax plus by plus cz plus d is equal to 0. So this looks familiar. This is just like our Cartesian or standard equation for a line. So remember, we've seen something similar before. Ax plus by plus c equals 0 is what we use to represent a line. Oops. Line in 2 space, or R2. And remember that our normal vector here was a b. And we talked before, how come I can't, like, why does this define a plane? Why does this define a plane and not a line? Well, it's because when we have our form here, the way this works is that we are giving a normal vector AB and then stating the line that's perpendicular to it and through a given point or whatever. But the problem here, and we talked about this previously, is that I have my three-dimensional line. Actually, I'll make this a little simpler here. I have my three-dimensional line, my three-dimensional vector A, B, C, and I can draw a line that's perpendicular to it, but I could also rotate it about this point and find another line that's perpendicular to it, and another line that's perpendicular to it, and this is kind of looking like a weather vane or something here, or a compass point or something. So I can have this whole, you can think of it like a disk that's extending, where this vector is perpendicular to everything here, and it goes below and extends below. So it's kind of like our side edge here. We have our vector here and our disk of parallel lines. There's a whole bunch of them, and it doesn't need to be a disk. It could be a sheet. And in fact, that's what we have here. It's a whole family of lines. In fact, it's a whole flat two-dimensional surface. And what do we call that? We call that a plane. And so what we're defining here is not a single line, because there are an infinite number of lines that will satisfy this condition in three-dimensional space. And so it's forming a plane. And so we can see in our diagram here, in order to define our plane, we can have our normal vector given by ABC, so heading from the origin perpendicularly through the plane. So the normal to the plane, normal is given by our ABC values in our Cartesian form. And then within that plane, we have our generic point P0 and our specific point P0, and we can define vectors and have direction vectors and stuff to travel around inside that plane. But for now, we're working with scalar form, and so I basically just want to know a single point and the normal vector. So let's take a look. Let's try applying this. What vector is perpendicular to each of the following planes? Well, let's think back to our form and to what we know about our normal vector. So what vector is perpendicular to plane A? Well, the normal vector, I just need my A, B, and C values, so it's going to be 3, 5, -2. Easy peasy. Next, N, our perpendicular or normal vector to our plane in B is going to be 2 and 0. Well, where does the 0 come from? Well, let's take a look. X, Y, and Z. Where's my Y component? It's still there. It's just multiplying by 0. Normally, we don't write that, but if it helps you, let's rewrite it with that 0. So B is also the same as 2x plus 0y minus z minus 16 equals 0. So my values I need are going to be 2 and 0 and -1. And let's take a look at C. Here our plane is given in the vector form. I can't really do much with that, but what I can do, we've already worked through a problem like this, is convert it Actually, sorry, vector form is fine. But what I'm going to need from here is my direction vector. So I have my plane, I have my direction vector here, m1 and m2, two non-collinear vectors, and I need the perpendicular, I need the vector that is perpendicular to the plane, and therefore perpendicular to both of these direction vectors which lie in the plane. So how do we do that again? Hopefully you've already seen the previous video and remember. Otherwise, you can think about it for a moment, and then I'll tell you that the answer is the cross product. So I think I have enough room to leave that there. So let's define our direction vectors, or our basis vectors. M1 was 5, -1, and 2. M2 was 1, 2, and -7. Let's find the cross product of those vectors. Remember, the cross product of two vectors is a vector that is perpendicular to both of them, which is exactly what we want here. So we're going to use cross product. Remember, just to be clear, because some people have struggled with this, dot product gives us a value that tells us something about the angle between our two vectors. Cross product is a vector. I'm going to say that again in case I messed up. Dot product is a number, is a scalar component, is a value that tells us something about the angle between our two vectors. Cross product is a vector that indicates a vector, or gives us a vector perpendicular to the two vectors we're considering. Let's use the Miss Spring method to find the cross product of m1 and m2, which will give us our normal vector n. So write our values twice, 5, -1, 2, 5, -1, and 2. And 1, 2, -7, 1, 2, -7. Let's do our chop chop. Goodbye. Group them. Let's do our crisscross. So multiply diagonally and subtract the values. So -1 times -7 is 7. -4 is 3. So that's our x component. Remember, we get our x, y, and z component. Multiply across. 2 times 1 is 2, minus -35. 2 plus 35 is 37. And multiply across. 5 times 2 is 10. Minus -1 is plus 1 is 11. Therefore, n is equal to 5, -1, 2, cross 1, 2, -7 equals 3, 37, 11. And did we need to do anything else here? Did we need to find the equation of our plane? No. It just said what vector is perpendicular, and we have found that, so we are good to go. In our next example question, we are asked to find the scalar equation of the plane. So remember, scalar equation, we just learned that. Ax plus by plus cz plus d equals 0 of the plane that has a normal vector. So we already have our normal vector. Awesome. And passes through the given point 2, 7, -5. And remember, we said earlier that to define the scalar equation of our plane, all we need is our normal vector and a known point. So let's see how we do that. So my normal vector is defined as 1, -2, 3. And like we said, that's going to be our A, our B, and our C value. And I know one point, so I know an x, y, z. And we can just call this point P. P is equal to 2, 7, -5, which is going to give us an x, y, and z value. So let's plug this into our Cartesian equation. And we don't know everything. So we know an a and an x value, b and y, c and z. We don't know the d value. That's what we're going to find out using substitution. So let's write out our equation. Ax plus by plus cz plus d equals 0. Let's plug in our values. A is 1, x is 2, plus b is -2, y is 7, plus c is 3, z is -5, plus d equals 0. That's not too bad. It's just a number of doing the matter of doing the math. So we're going to have 2 minus 14 minus 15 plus d equals 0. And we're going to have minus 27 equals d. I'm skipping a few steps for the sake of sanity. Actually, sorry, that's wrong. This is why you shouldn't skip steps. Negative 27 minus d equals 0. Sorry, plus d equals 0. So negative 27 equals negative d, or d equals 27. All right. So what did we do here? How did we actually do this? Let's write out our steps. So step 1, find a, b, and c from a normal vector. Next, find x, y, and z from our point. 3, sub in to our scalar equation and solve for d. And step 4, state our equation, which we haven't actually done that yet, so let's do that now. Therefore, the scalar equation, of this plane is, let's see, a is 1, so I don't need to write the 1, so I can just write x, plus b is negative 2, so plus minus 2, so minus 2 y. C has a value of 3, so plus 3z, and my d value is 27, plus 27 equals 0. All right, looking good, and let's just zoom out so we can see the whole thing and not have the watermark in the way. Looking pretty good. Let's move on and see what's next. In our next example here, we are asked how can we find the scalar equation of this plane. So we're given a plane here in vector form. We have our position, we have 2 direction or basis vectors. Hint, we've already found that n is equal to 3, 37, 11. And we found that 2 pages ago on that example, so you can scroll back up and double check. But basically, as a quick reminder, we just found, we found n by finding the cross product of our 2 direction vectors. So 5, negative 1, 2, cross 1, 2, negative 7. So I'm not gonna redo that. You can scroll back up or rewind in the video to review that process if you like. So what do we need for the scalar equation? Well, we said previously we need a point and we need a normal vector, and we have those. So let's just indicate them here. We have our point from here, 1, 0, 3, and that's my x, y, and z value. And I have my normal vector, 3, 37, 11, and that's my a, my b, and my c value. And let's write our scalar equation and solve for d. So my scalar equation, ax plus by plus cz plus d equals 0. Plug in our values, which we know, 3 times 1 plus 37 times 0 plus 11 times 3 plus d equals 0. 3 plus 0 plus 33 plus d equals 0. 36 plus d equals 0. D equals negative 36. So let's write out our steps. What did we just do? We didn't actually do this first part, but that's what we would do if we hadn't solved this previously, and that's find our n vector using m1 cross m2, sub our known point p and n values into equation to solve for d, and then state our equation or define our plane. So what's our equation? Therefore, the equation of this plane is a value is 3x plus b value is 37, y plus c value is 11, plus d value we just find is negative 36 equals 0. All right, looks pretty good. Next up, what else can we do with our skills? Given the plane, 4x minus y minus z plus 10 equals 0, and that's our Cartesian form once again. A, we are asked to find 2 points, A and B, on the plane. And B, show that the vector AB is perpendicular to the normal of the plane. Why must this be true? We'll get there in a minute. So we need 2 points on the plane. Let's sketch our situation here for a moment. So I have my plane, pi, and I'm going to have 2 points on my plane, A and B. So 2 points on the plane. So a point must satisfy this equation. Just like we've seen, once again, originally in grade 10 and stuff with linear equations or any kind of function, a point that exists on the plane or a point that exists on the line are values for x and y or x, y, and z that allow our equation to be true. And that's just what it means to solve. So let's find a few values here. And when we worked with regular lines before, we talked about like finding the x-intercept by letting y equal 0, or finding the y-intercept by letting x equal 0. I'm not sure I said that right. I'm going to say that again. Find the x-intercept by setting y equal to 0. Find the y-intercept by setting x equal to 0. And we're going to do something similar here. So for A, I'm going to set up a table of values, x, y, and z. And in the first case, I'm going to let x equal 0 and y equals 0. So let's plug those values into our equation and solve for our missing value z. So 4 times x of 0 minus y of 0 minus z plus 10 equals 0. Negative z equals negative 10, or z equals 10. So I know one point on my plane, and that point is 0, 0, 10. Next, I can let x equals 0 and z equals 0. So write my equation. 4 times x is 0, minus y is what we're finding, minus z is 0, plus 10 equals 0. I'm going to get negative y plus 10 equals 0, or y equals 10. So the point 0, 10, 0 is another point that lies on my plane. And we only needed to find 2 points, so technically we're done, but we could do this another way as well. So let's just show that we are here to learn, not just answer the question. So let's let y equals 0 and z equals 0. So we're going to have 4x minus 0 minus 0 plus 10 equals 0. So 4x plus 10 equals 0. 4x equals negative 10. X equals negative 10 over 4, or negative 5 over 2. So the point negative 5 over 2, 0, 0 also exists in our plane. We don't need it. The question only said to find 2, but we can also do that. So therefore, to answer A, 2 points on the plane are, and I'm just going to label this my point A, and B, point A, which was at 0, 0, 10, and point B, which was at 0, 10, 0. Cool. That's A. What do we need to do for B? Show that the vector AB is perpendicular to the normal of the plane. Why must this be true? Well, let's start by stating what those pieces are. So I'm going to have my normal vector, and remember that's just my ABC values for my equation up here. So my normal vector is defined as 4, negative 1, negative 1. My vector AB, so remember I'm just taking my values from A and B here, x, x2, x, so like B1 minus A1, B2 minus A2, and so on. So I'm going to have a value of 0 minus 0 is 0, 10 minus 0 is 10, and 0 minus 10 is negative 10. So this is my vector running from point A to point B. And in order to prove if these are perpendicular, we're going to use, what are we going to use? The dot product. So let's find n dot AB, which is going to be equal to 4, -1, and -1 dot 0, 10, and -10. And remember, we just find the product of each component, the x, y, and the z, and add them. So 4 times 0 is 0, plus -1 times 10 is -10, plus -1 times -10 is 10. And we see pretty quickly that that equals 0. N dot AB equals 0. Therefore, N and AB, actually, simplify that a little bit. Therefore, N is perpendicular to AB. And the question said, why must this be true? Well, we just proved that. We kind of know this intuitively. If A and B lie in the plane, and we have some vector lying in the plane, and we have the normal vector, which is already given in the equation of the plane. So I have my vector n. We already know that it's going to have to be perpendicular, and we're just proving it here. So in order to finish this up, all we're going to just say is, since n is perpendicular to AB, or sorry, I'm putting my conclusion before my evidence. So since n dot AB equals 0, therefore vector AB is perpendicular to the normal. And I should probably write that out in words, but I just want to save space here and be done with this. So I'll zoom out so we can see the whole thing. Let's describe our process. So I'm going to move my little sketch here over. What were our steps here? Let's see if we can go back and describe them. Step 1. We found 2 points in the plane. And we did that by setting 2 components to 0, x, y, x, z, y, z, and solving for the remaining value, just like when we find x and y intercepts. Next, we found the vector. So 2 points, A and B. Next, we found the vector. Then we found n from our equation. And then we found dot product to confirm that they were perpendicular. All right, cool. Couple more examples to go. Let's keep going. And actually, before we move on, I'm just going to add one thing, and I'll just say this out loud. I don't really have room to write it, and that is that this normal vector that we just found is perpendicular to every direction vector in the plane. So any vector that's in the plane, so whether that's going to be going this way or this way or this way, and this kind of looks like that diagram we drew earlier. And I mean, it doesn't have to be located here. It could be over here, any line in the plane, any direction vector. They're all within this flat surface, which the normal is intersecting at 90 degrees. So any direction vector in the plane will be perpendicular to that normal vector. All right, moving on. Another example. Determine the scalar equation of the plane that passes through point 4, -6, 7, and has a normal parallel to the z-axis. So once again, how are we going to do this? We're going to find our scalar equation. So our ax plus by plus cz plus d equal to 0. And what do we need? We need a point and a normal value n, and we have our point. So I have my x, y, z value, and I have my normal vector, 0, 0, 1. Well, wait, where did I get that from? Well, what do we know about our direction vector? We know it's parallel to the z-axis. Do I know any vectors that are parallel to the z-axis? Yeah, remember I had my I, my j, and my k. The unit vector parallel to the z-axis, which we've previously used to represent the z-axis, so we can just use that. So that is where that is coming from. And so I know my A, my B, and my C values. So let's plug that into our equation. I don't need to rewrite it again. Let's just plug our values in. So A is equal to 0, X is equal to 4, plus B is equal to 0, Y is equal to negative 6, plus C is equal to 1, Z is equal to 7, plus D equals 0, 7 plus D equals 0, D equals negative 7. So therefore, the equation is Z minus 7 equals 0, or we can just consider it as Z equals 7. Well, how does that work? How can I just define a plane as a single point? Well, you can imagine if I had my Cartesian planes X, Y, and Z is 7. Basically, I'm just going to have my flat plane where it just intersects at 7. So, you know, the line going through the plane here, this is my z-axis, and this point right here is 7. So what that means is I can choose any x or y values that I want as long as my z value is 7. So this means that x and y can have any value. So we can have 0, 0, 7. We can have 1, 1, 7. We can have 1,000, negative 32, and 7. Any numbers we want. It really doesn't matter. And we can relate this back to a similar situation we've seen before when dealing with lines. Whoops. So you know when we work with lines, normally we have y equals mx plus b. And that's our slope y-intercept form of our line equation. But sometimes I have stuff that's just like x equals 2 or y equals 1. And you're like, well, what does that mean again? Remember, these are just lines with no slope. Or sorry, it's a line with no slope or a line with infinite slope. So these are our horizontal and vertical lines, which once again, you specifically looked at in grade 10. So if we have our x and our y-axis and we have x equals 2, we can have any possible value for y that we want as long as x equals 2. Or if we have our y is equal to 1, I can have a line with any possible x value I want as long as y is equal to 1. So basically this is similar to horizontal and vertical lines. So our special cases of lines, and we've just seen our special case of a plane. Oops, and let's move that up so we can actually see. There we go. We're getting closer to the end of our note. Let's answer a few important questions and cover a few important concepts, see what we know already and what we maybe will be explaining as we move forward. 1, what does coplanar mean? Coplanar means to lie in the same plane. So it means it's going to be parallel with the plane. The plane or level with the plane. And if we were to sketch our plane, pi, this means any vector or any direction, any vector that's going to lie in the plane. So it's lying on the surface of the sheet, or it's above and below and parallel. All right, how many points do we need to define a plane? We've talked about this before. And I do recommend that you pause to try to answer these questions before watching me go through it, just to test your own knowledge. We need 3 points, but they must be non-collinear. 3 non-collinear points. So something like this is good. Something like this, where they all lie on the same line, is bad. Question 2b. Will any 3 points be sufficient to define a plane? No, we just explained this. They must be non-collinear. And so remember, we have to test. If we're given 3 random points, we need to test to make sure they're not collinear. What does collinear mean? It means parallel. It means lies in the same line. So if I can draw a straight line through all of them, kind of like a line of best fit, but like exactly, so it actually goes through them. And finally, how many points do you need to define a line? Any 2 points. So any 2 points can define a line. 3 points can define a plane, as long as we've made sure that they are not collinear. Now that we've talked about what coplanar means, let's solve some problems involving that concept. Solving some problems involving coplanar points. Are the 4 points, and we're going to label these as we go, so we're going to have point A, 1, 0, 2, and point B, and point C, and point D. I'm not going to read all those out. You can see them for yourself. Are they coplanar? Prove or disprove this by first finding the equation of a plane. First finding the equation of a plane. So we're going to use 3 points. We know any 3 non-collinear points are coplanar. So step 1, let's choose a point, and let's find the equation of a plane. Sorry, and by a point, I mean 3 points. So let's write our steps off to the side as we go to summarize what's happening here. So step 1, we are going to choose 3 points to find the equation of a plane. To define our plane. And to visualize what's happening, so we're going to take our point A, our point B, and our point C. Point A was at 1, 0, 2. Point B was at 7, 12, negative 16. Point C was at 2, 22, 4. And this is going to give us the pieces we need to define our plane using our Cartesian equation, because remember, we need a point, which we have, and 2 direction vectors, which we'll be able to find quite easily. So let's go ahead and do that. So we're choosing 3 points to define a plane. So we're going to need a point. And we're going to need our direction vectors. For my point, I'm choosing to use point A. So 1, 0, 2. For my direction vectors, M1 is going to be my vector AB. So remember, to find that, I'm just finding the difference between the x values, the y values, and the z values. So 7 minus 1 is 6, and 12 minus 0 is 12, and negative 16 minus 2 is negative 18. And my second direction vector, M2, is equal to my vector AC. So finding the difference between the x, y, and z components. So 2 minus 1 is 1. 22 minus 0 is 22. Oops. And 4 minus 2 is 2. All right, great. So I have 2 direction vectors and 1 point. Now that I have my direction vectors, I need to make sure that they are not collinear. So we found our direction vectors. We tested to see if they were collinear, or at least we're about to. So remember, we just look at the ratio of one vector over the other, make sure they aren't scalar multiples of each other. So 6 over 1, is that equal to 12 over 22? And is that equal to negative 18 over 2? Clearly not. So we know that m1 is not equal to some scalar multiple of m2, so they are not collinear. That's good. That means we can use these 2 direction vectors to define our plane. And what I'm going to do with them, remember, I want to find it in the Cartesian formula, which means I need the normal. How do I find the normal vector to 2 other given vectors? Use the cross product. So we tested collinear. Step 4, we're going to find n using cross product. So n cross, n equals m1 cross m2. Let's plug those values in. So m1 is equal to 6, 12, negative 18, cross 1, 22, 2. And remember, to find that, we'll use our Miss Spring method. So let's write that out. Write out my points twice. So 6, 12, negative 18, 6, 12, negative 18, 1, 22, 2, 1, 22, 2. So write out twice, chop, chop, and crisscross. Once again, I'm not showing all my work, but I'll show some of it. So we're going to find our x, y, and z components. So I'm going to cross 24 minus, I'm going to need my calculator for this one. That's going to equal 420, comma, negative 18, minus 2 times 6 is 12, so negative 30, and 6 times 22 minus 12 is 120. And notice we got pretty big values here. If you're looking at the completed copy of the note, there wasn't another way of doing this. What I could have done is this direction vector here, m1, I could have expressed it as, if I divide out the 6, 1, 2, negative 3. I missed that step, so I'm not going to go back and do that, but we could define our m1 direction vector as this vector right here. That's fine. It's just a scalar multiple of the one I found the other way, so we'll get the same result either way. I just have to deal with extra big numbers right now as I go, but I'm going to stick with it and keep going. Actually, I'm going to go back and fix that up. So the way I was doing it was fine. There's nothing wrong. It's just annoying. So I'm going to go back so we can do this with some smaller numbers. So I'm not going to edit this video. I'm going to leave that in. I make mistakes sometimes, or it's not even wrong. It just makes our life a little harder. Let's fix it up and do this a slightly easier way. So after I defined my vector m1, my direction vector m1, what I could do is notice that I could factor out the 6. And I can just use this vector instead. And so I could redo my collinear test. I guess I might as well. 1 over 1 equals 2 over 22 equals negative 3 over 2. Once again, not collinear, not scalar multiples of each other. Doesn't change anything. Let's find our normal vector. So m1, we got a little bit easier numbers to work with now, is 1, 2, negative 3, cross 1, 22, and 2. Let's use our cross multiplication method. 1, 2, negative 3, 1, 2, negative 3, 1, 22, and 2, 1, 22, and 2. Chop, chop. Goodbye. And let's do our crisscross. 2 times 2 is 4. Minus negative 66 gives us 70. 3 minus 2. Sorry, negative 3. Just got a little bit covered there. Make that a little more clear. Negative 3 minus 2 is negative 5. And Z, 22 minus 2 is 20. So there is my cross product, and that is my n value. So n, my normal vector, is equal to 70, negative 5, 20. And once again, we can find a scalar multiple of this. It'll be equivalent, so I can factor out 5. And I can rewrite this as 14, negative 1, and 4, just to make our life a little bit easier. So the 5 isn't really, like, I don't want you to be confused. Why is it disappearing? It's just because we don't need it. These are collinear vectors. It doesn't matter which one I use. And so by factoring it out, I'm just keeping this chunk. I don't need the 5 anymore because I found an equivalent vector that's in like lowest terms, so to speak. All right, now that I have my normal vector and I know a point on the line that I can use, let's go ahead. Our point was up here. Let's go ahead and actually find our scalar equation. So, scalar equation, ax plus by plus cz plus d equals 0. A comes from our normal, so it's going to be 70, and x is my point, so 1, plus b from my normal is negative. Sorry, I forgot that we simplified. All right, so I'm going to highlight this so I don't make this mistake again, and it's a mistake you might easily make as well. This is the point we're using. This is the direction vector we're using. I was still using this one. Let's use our simplified one. Let's try this again. So this is my x, y, z. This is my a, b, c. Let's plug these values in. A is 14. X is 1. Plus b is negative 1. Plus y is 0. Plus c is 4. Plus z times z is 2. Plus d. So we're doing this to solve for d, and we get 14 plus 0 plus 8 plus d equals 0. And we find that d equals negative 22. So we can finally state our equation. Therefore, equation is a is 14, x, b is negative 1 minus y, c is 4 plus 4z, d is negative 22 equals 0. Is there anything else we have to do in this question? What did it ask us to do? It said, are the 4 points coplanar? We don't know yet. We've just used 3 points to define a plane. Now we have to see if the 4th point lies on that plane. So find n using the cross product. Let's tidy this up a little bit. Solve for d and state the equation. And 6, test if 4th point lies on the plane. So we've defined a plane. We know our 3 points were non-collinear. We defined a plane. Now let's see if that last point number 4 lies on the plane using a left side, right side check. Test. Does point D, which had the coordinates 11, 8, and negative 31, lie on the plane? I'm running out of room here, but I think I'll have enough room. If D lies on the plane, then this value must satisfy our equation. So if D lies on the plane, then 11, 8, negative 31 will satisfy our equation. So if I plug those values into the equation I just found, I'll have a valid result. So let's do our left side, right side check. left side is 14 times x, which is 11, minus y, which is 8, plus 4z, which is negative 31, minus 22. Let's calculate. What am I going to get? 14 times 11 minus 8 plus 4 times negative 31 minus 22 equals 0. And my right side of my equation also equals 0. Therefore, left side equals right side. And there we can say, therefore, make myself a little bit more room here. Therefore, point 4 or point D lies on the plane, and therefore points A, B, C, and D are coplanar. So we defined a plane using 3 of the points after proving they were non-coplanar, and then we tested to see if our 4th point also could be found on that plane. All right, we got one final example in this lesson, and then we are done. We will be masters of the equation of planes. In this example, we are asked to determine the values of k so that the points given are coplanar. So let's label these A, B, C, and D, and we basically have to do the same test as last time, and we're going to solve a value for k that allows this to be true. So first step, use 3 points to define our plane. All right, so let's find the equation of the plane using our first 3 points. So just like before, A, B, C. A is going to be my point vector. AB is going to be my first direction or basis vector. Vector AC is going to be my second one. So vector M1, which is equal to AB, and I find the difference between the X, Y, and Z components. It's going to be 1, 1, and 4. And direction vector M2, which is equal to AC. Find the difference between those X, Y, and Z components is going to be negative 5 and negative 2 and 7. And we need to make sure that those are not collinear. So let's take a look. Let's do our test. 1 over negative 5, 1 over negative 2, 4 over 7. Obviously not collinear, so M1 is not a scalar multiple of M2, which means we can use them to find our normal vector. So I'm going to take the cross product. And I'm not showing quite as much work this time because I already did that previously. So I'm going to find my normal by finding the cross product of M1 and M2. So I'm going to list my coordinates and show my work over here. 1, 1, 4, 1, 1, 4, negative 5, negative 2, 7. I didn't give myself enough room here. 1, 1, 4, 1, 1, 4, and negative 5, negative 2, 7, negative 5, negative 2, 7. Chop, chop. A little too aggressive with the chopping there. Let's find our X, Y, and Z components. Remember, once again, cross product is a vector, which is perpendicular to the 2 vectors we're looking at. So 7 minus negative 8 is 15. And negative 20 minus 7 is negative 27. And negative 2 minus negative 5 is negative 2 plus 5 is 3. And so our n value over here is equal to 15, negative 27, and 3. And we notice right away that there is a common factor we can factor out. So I'm going to factor out my 3. So 5 negative 9, and 1. And remember, scalar multiples of the vector, of the direction vector, point in the same direction. They're collinear. So I can just use this piece instead. So I'm going to define my vector n now as 5, negative 9, and 1. Remember, that gives me my a, b, and c value for my point. And I have an x, y, and z value. I'm going to use point A. Let's plug that into our equation. ax plus by plus cz plus d equals 0. Sub in our values. A is 5, x is 1, b is negative 9, y is 3, c is 1, z is also 1, plus d equals 0. So 5 minus 27 plus 1 plus d equals 0. 6, negative 21. Negative 21 plus d equals 0, or d equals 21. Therefore, our equation is a was 5, b was negative 9, c was 1, d was 21. So we found our equation. Cool. Final step. Find k value to allow point to lie in or on the plane we just defined. So my steps aren't very detailed here, but it's the same stuff we just did in the previous question, more or less. So let's see what we have to say about this. If my point D, which is 6, 1, and k, lies on the same plane, it must satisfy the equation. So I have to plug those values into the equation I just found and get the same result. So left side must equal right side. So let's plug our values in and solve for k. So this will be my x, y, and z. I have my equation. Let's plug it in. So 5, x is 6, minus 9, y is 1, plus z, which is k, plus 21 equals 0. Everything is defined. We only have one variable left. We have one variable. We have one equation. That's enough information to solve. So we're going to have 30 minus 9 plus k plus 21 equals 0. 30 minus 9 is 21. 21 plus 21 is 42. So k is equal to 42. So therefore, negative 42. Got to be careful. I should be showing my work, so this is what happens when you skip steps. Finally, the question said, determine the values for k so that the points are coplanar. Therefore, the 4 points are coplanar when k is equal to negative 42. And that is the end of our note on dealing with the scalar equation of planes and our final section here on dealing with coplanar situations.